color features. Most devices capture images in RGB color space. Screens and monitors produce colors by means of red, green, and blue light. Scanners and digital cameras also work with RGB colors. The RGB is highly correlated. A simple value change in either of these channels changes the color. It is non-intuitive, means how do we define skin color as RGB components? It's also device dependent. What do you mean by device dependent color space? It actually varies with scanner or monitor characteristics. Such color space depends on the equipment and the setup used to produce it. For example, the color produced using the pixel values RGB will alter as you change the brightness and contrast on your display. In the same way, if you swap your monitor, the red, green, and blue phosphors will have slightly different characteristics and the color produced will change. Other color spaces can be obtained by color space transformations from RGB. One of the motivation can be to transform the device-dependent RGB to a device-independent color space. How many types of color spaces are there? The human visual system based, that is the SVS. It's motivated by the principles of human visual system, the way we see, the ability to see and perceive. According to the trichromatic theory, humans have three cones of wavelength sensitivity, L and S. The Herring's opponent color theory. The opponent color vector consists of achromatic component, that is white-black, and two chromatic components, red and green and yellow-blue. Respond to opponent color stimulus. One of the example is OTA color space. Another theory behind this HVS is Isaac Newton's color cycle. It mentions the hue and saturation for describing colors. The disadvantage of HVS based color space is device dependent, as we have discussed in the last slide, and there is no perceptual uniformity. What do you mean by a perceptual uniformity? A system is perceptually uniform if a small perturbation to a component value is approximately equally perceptible across the range of that value. RGB is perceptually non-linear. This means that equal differences in the RGB values do not correspond to equal differences in the perceived color. A small numerical change in the red can lead to a much bigger visually noticeable change, and a large numerical change in R can also happen that it creates a very little noticeable change. Another one is the application specific color spaces. Printing systems, the CMYK is one of the color space. TV systems use YUV and YIQ. Photo systems, photographic systems, Kodak Photo YCC. The third one is the ideally used color space for various image processing tasks. Because of the advantage it has, such as device independency and perceptual linearity. It is defined by the International Commission on Illumination CIE color space. The example of such color spaces are CIE XYZ, L star U star B star, L star A star B star, or lab colors. The colors can also be categorized as additive color and subtractive color. Additive color systems start with darkness and is a method to create the color by mixing a number of different light colors, with shades of red, green and blue being the most common primary color. The light sources of various wavelengths are added in various proportions to produce a range of colors. Say for example here, the application is computer monitors, televisions, projected color lights as in theaters. Here you will see this is a red, this is green. It adds red plus green to show a yellow color. Such type of applications are seen in theaters. The subtractive color. The commonly used subtractive primary colors are cyan, magenta and yellow. If you overlap all three in effectively equal mixture, all the light is subtracted, giving black. It starts with light, presumably white light. Colors are removed from the white light, that is subtracted to make different colors, or the black, that is no light. Applications are color printing, paints, dyes. Let us see an example where the application requires to scan. As we know, the scanning happens in the RGB color space, and finally the scanned output has to be printed, which is in CMYK color space. Let us see the advantages of using the color space, which is device independent. If we do a color transformation without the lab values or the ICC profiles, then this color, when scanned by 3 scanners, gives 3 different combinations of RGB which are close to each other, and then it's transformed to CMYK for different printers. Hence, this color transformation is device dependent and the output may not look same. The next option is using the ICC profile. The ICC here is a group of vendors who define the ICC profile format, that is cross-platform specification, which allows the third-party vendors to develop profile tools and applications supporting the standard. The members include Adobe Systems, Apple Computer, Kodak Company, Microsoft Corporation, Silicon Graphics, Sun Microsystems, etc. These companies have committed themselves to fully support this specification in their operating system, platforms, and applications. Hence, if we go ahead with the scanners with ICC profiles, then all the outputs for this light green are same. So the color transformation with lab, which is the device independent color space, using the ICC profiles, the light green definition remains same, and the printers also take the input same and gives the output same. So the quality of the color print will be same for this particular input. The image planes can be visually represented. The grayscale images, the RGB, maximum we can visualize a 3-dimension space with the colors. This is LAD, HSV. The CMYK cannot be visualized as one picture, so each of the channels, a CMYK, has been represented here. Researchers have also come across new hybrid color space which takes each channels which are advantage to their applications, merge them and do a dimensionality reduction and produce a hybrid color space. Next, let us see what is a texture. The texture is very ill-defined. It's still an open challenge to model any types of texture. The regular textures are easier to model and use it in the applications, but real life natural images do not have regular textures. In a literature survey, when the texture analysis is done, textures come into picture for various tasks such as texture classification, object detection based on the textures, shape formation, context-based image retrieval, texture characterization, and texture segmentation. So, presently in the research community, the texture plays a very important role independent of any application domain, paving way to application independence. What is texture? It refers to spatial distribution whose nature can be random, pattern specific, or directional. Characteristics depending on the size, the granularity, directionality, orientation, random, or regular. The texture primitives can be multi-textural. Small primitive called the microtexture, large primitives called the macrotexture. In this picture, we can see that This area forms large stones because the humans perceive them to be rocks, but it is irregular in nature, and hence how do we define this texture and perceptually group them under rocks. Similarly here, the colors, the shapes, though they are similar, colors vary, texture is almost similar. The category for texture analysis, basically there are two types: spatial based and model based. The spatial based further divided into statistical, structural and hybrid. The statistical is applicable to all but less intuitive and needs prior info to characterize. The structural suits for macro texture and regular textures but doesn't fit the natural images. The model is a powerful tool based on probability model. Estimation of model coefficient is difficult in this type of texture analysis. Again, coming to the data sets. As we have seen in the previous lecture, for segmentation we have to take some standard data sets to perform our experiments, execute our algorithms. Similarly, for texture analysis research, there are standard data sets which can be categorized into two. One is the grayscale image products data set, but trend has shifted to the color based texture, color texture characterization Vestex dataset. The applications for the color texture analysis can be found in industrial application for grading the products, for visual inspection and CBIR. So this is all about the texture. Next, we will see how to do a color texture feature integration. Thank you.